Okay, so in this video, we're going to look at how to use power series to solve ordinary differential equations. Now, there are some functions, some ODEs that we can solve without using series solutions, but there are going to be occasions where we need some alternative techniques because they don't fit some of the really basic constant coefficient or Cauchy-Euler type form. And so that's what we're going to be trying to address here. Now, our first example is going to involve a simpler case where we can sort of confirm our results, but we're also then going to go on and do some examples that can only be done this way. So let's first define some terms. So when we are dealing with a function that has to be solved by series solutions, we have two kinds of points that we have to consider. So an ordinary point is a point in the standard form of our ODE that all of the functions are defined at every point. And a singular point, which will come into play in our last example, is a point at which some of these functions are actually not defined, but if you multiply the function by a factor of x minus the place where the point is undefined, then you can generate a function which is defined, at least it has the limit that exists, and therefore we can proceed from there. So we're going to look at one example that involves a singular point. Most of the examples we're going to look at are going to involve, we're going to do the power series expansion at an ordinary point. But when these singular points do come up where some of these functions might not be defined everywhere, we're going to run into an issue, and we'll see that actually play out as we do the series solution. And then the very last example, we'll talk about how to resolve that potential problem when there is a point of discontinuity. How do we get around that? All right, so the first kind of thing to kind of keep in mind is that our general solution for our ODE is going to take the form of a power series. So we have a constant, we have a coefficient that is going to depend on the term, the nth term, 0, 1, 2, 3, and we're going to have a simple power series x minus the center. So for a lot of our examples, we're going to be centering it at 0, but you don't have to center it at 0. This process will work if you're trying to center your solution at some other point. But this is going to be the general form of our solution. It's going to take the form of a power series. And in order to substitute it into our ODE, we're going to need to take some derivatives. So here's my original function. If I take the derivative, then I'm going to bring my power down. So there's my new n, and then I'm going to reduce my power by 1. Keep in mind that since this expression to the 0 power is a constant, when you take the derivative of a constant, you get 0, so you lose the n equals 0 term. That's important as we go forward. The second derivative, then, we start with the first derivative, we bring our n minus 1 power down, we reduce our power by 1, and we lose another term of our, we start now at n equals 2, because the n minus 1 term, and when n is 1, is now an expression raised to the 0 power, which is a constant, and therefore it disappears. Same thing for the y triple prime. We bring our n minus 2 down, we reduce our power, but then we start at n equals 3 because the n minus 2 term was now a constant to start with. So these are our standard derivatives that we're going to use as we do these examples. Now, we're also going to need at some point to reset our series back to 0, even though they start, some of them, at 1 or what have you. Another skill that we're going to need is to be able to reset them. to an equivalent series starting at n equals 0, because we're going to want all of our series to start at the same point. Now, this is not something that you want to do before you do the substitution. It'll be something we do after we do the substitution. But still, just as a matter of a skill, if you want all of these n's to be the same number when you plug in n equals 1 in this expression versus n equals 0 in this expression, if you back the starting value down 1, you have to add 1 back into the formula. So here, when n equals 1, this is c sub 1 times x minus 0 to the 0. But here, when n is 0, you get c1, 0 plus 1 is 1, x minus x of 0 to the 0. So this expression starting at 1 is equivalent to this expression starting at 0. So again, all we did was I backed this index starting value down, and I compensated for it by bumping up my n expressions in my formula by adding 1 back inside the formula. So similarly, if I start at n equals 2 and I want to restart at n equals 0, I'm going to have to bump all of my expressions where n up by 2. So n will become n plus 2. This n becomes n plus 2. N minus 1 becomes n plus 2 minus 1, which is n plus 1. And n minus 2 here becomes n. Now, again, we're not going to do this before we do the substitution, because in some of our problems, we'll be multiplying by x. And so in order to get all of our powers to be equivalent, we may be starting at slightly different places. So, but this is how this would work when we have it and we're ready to go. All right, and then the other thing that we may need to do is, if we have different starting values for our indices, we may need to pull off individual terms. So the way that we do this is you write out the terms, and then you can, if you take out the n equals 0 term, the remainder of the sum will then start at n equals 1. If you pull out 2 terms, then the remainder of the sum will start at n equals 2. You don't change the formula at all when you do this, but we're pulling out terms because we're trying to match inside of our process. We're going to have to match both the power and the starting value of our sums in order to combine them. And so there's different places where we have to make some adjustments. Now let's look at some example problems. So I started as an example problem with something that we could actually solve by other means so that we can use it to check our answer. So we're going to try to solve this second order constant coefficient differential equation around the point x equals 0. So we're going to set our y equal to this summation, and x, since x sub 0 is 0, that expression just becomes x to the n. And so this is our sum. And then we need to take our derivatives. So the second derivative, I didn't write down the first derivative, but the second derivative, we start at n equals 2, our constant, our n from our first derivative, our n minus 1 from our second derivative, x to the n minus 2. And then we're going to substitute expressions for both y double prime and y into our differential equation. And when we do that, this is our second derivative times 4, and this is our y equals 0. Now, the first step is to bring all the coefficients inside the summation. And in order to do that, this is referring to this 4 on the outside. So we're going to bring that inside the sum. Again, any stray coefficients that were in the original differential equation, you just bring them inside your summations. Whether you multiply by the sum or multiply by individual terms, you get the same result. Step 2 then is going to make all of the exponents the same. So in order to add these together, one of the things that we require is that these x's be x to the n in both formulas. So sometimes, depending on whether you've multiplied by x, there's something in different places. This may require that you rewrite this as x to the n plus 1 or something like that, but you want them to match. But since I have x to the n here, I'm going to make them x to the n. So the second summation is already in that form, but I need to change the index, as we saw earlier, to make this, by taking this down to 0, I can make this x to the n again. And so that's what I've done here. I've reset my index to 0, and everywhere I had an n, this becomes n plus 2, n plus 2, n minus 1 becomes n plus 1, and x to the n minus 2 becomes n. So now I have my x to the n's in the same place. Now step 3 is to make sure that in order to combine terms, that the summations are starting at the same number. In this case, by adjusting the x to the n's, we have already made that the case, so we don't need to do anything else here. But if we had, let's say, one of these starting at n equals 1 and one of them starting at n equals 0, we would pull out the one that had the extra term so that they both started at n equals 1. We'll see that in a future example, but for right now, they already agree. So this step, we don't have to do anything. And then finally, we're going to, because these are now all x to the n's and our indices start at the same value, we can rewrite this as a single summation and combine the coefficients together inside that single sum. So we've combined them into a single sum and we've factored out the x to the n. Now it's still inside the sum, but we've collected the coefficients from the two summations in one expression. And in order for this expression to be 0 all the time, for any value of x, it's these coefficients that have to be equivalent to 0. So we're going to pull that out, and we're going to rewrite the c sub n plus 2 in terms of c sub n. So move the c sub n over, divide by all these other constants, and we get this expression. So what this is telling us is that if you start with an even number, then the next even coefficient will be based on this formula. But if you start with an odd c sub 1, for instance, then the next odd index will be based on this formula. But the even ones and the odd ones are not they're not related to each other. The coefficient for C0 and the coefficient for C1 are independent. But we have this formula that will generate those coefficients once we have the first one in the term. So in the series. So what we're going to do is we're going to start calculating some of these coefficients to see if we can establish a pattern based on our initial values. So I've created a table here. We're going to start with n equals 0 and find C2 in terms of C0. And I've also started with n equals 1, that's that second sequence, and C3 then will be based on C1. And then we can keep going. Now, the algebra gets a little bit more complicated because we always want our final answer to always be based on C0 or C1, because those are the generating constants for our function. So when n is 2, we can calculate C4 using C2, and then plug in the value for C2 from our previous expression to get an expression for C4 that involves only C0. Same thing for n equals 3. We're going to calculate C5 from this. We start with C3, generate the formula, and then replace C3 with the expression for C3 based on C1, and then do some arithmetic. And we would continue in this fashion for n equals 4, n equals 5, and so on, long enough to create a pattern. So let's see what kind of pattern we have. we have here, this looks like 4 times 2 factorial. And then here we have 4 squared and 4 factorial, and then 4 cubed and 3 factorial, and 4 to the 4th and 8 factorial. I'm sensing a pattern. So that's one thing. Same thing on this side. This looks like 4 times 3 factorial. And then this is 4 squared times 5 factorial. And then this is 4 cubed times 7 factorial. So again, these are all the odd factorials, but the powers of 4 are only going up by 1. Actually, that should be 4 to the 6th right there. Or 4 to the 5th right there. That's a little typo. But you can also think of this as, since these factorials are going up by 2s, you can think of these as 2 squared, in which case they are going up by 2. The powers of 2 are going up by 2 as well. Now, in this sequence, we have odd factorials. In this sequence, we have even factorials. So if we look at our C0 terms, again, we can see that we have our 2n factorials, 0 factorial, 2 factorial, 4 factorial, 6 factorial, etc. And then these 4s I can rewrite as 1/2 squareds in the denominator. And that will get me my 2n power as well. And then my x's are going up from x0, x2, x4. They're going up by powers of 2 as well. I'm C0. And then for the second sequence, again, I have my odd factorial, so that's my 2n plus 1 factorial. And then again, my 4s are really 2 to the 2n's. And I pulled the 2 out here in order to make this 1/2 x to the 2n plus 1, just to make the math work out a little bit more nicely. Now, part of the reason that I did that is because I know what the solution was based on my constant coefficient process for my second order ODE. I know that the formula is going to depend on sine 1/2 x and cosine 1/2 x. And so rewriting it in this form is consistent. This is my sine function, and this is my cosine function. The fact that this C1 is an unknown constant means that I don't really care about that extra 2 out there. It's still basically the same equation that I would have had before, but I have my 2 solutions now. Y1 is this sum, which is equivalent to my cosine at 1/2 x, and y2, this is my second solution. Again, one unknown coefficient times sine of 1/2 x. So that's sort of the simple case, because I actually know what those solutions are and I can check my work. But what happens if I don't have a solution that I can find by other means? How does that differ when I do this? So our second example is going to involve a case where we're multiplying some of the terms in our differential equation by x, but not in places that would make it Cauchy-Euler. And so the series solution process is kind of our main way of solving these. Unless we can guess a solution, we could use reduction of order. But if we can't guess a solution, then series solutions are the way to go. So again, we're going to try to solve this with a series centered at 0, partly because I want to illustrate what happens when you do that. If you put this in standard form, your y prime, the function multiplying your y prime term, is not going to be defined at 0. And so we're going to see that that's actually going to be a singular point, and we're going to run into problems. But then we will solve those problems at the end in our last example, we'll talk about a technique we can use when we are dealing with a singular point like this with our series solutions. So, but we're going to start it just using the same process that we did before and see what kind of impact these x's have on our process. So same thing, since we're centering it at 0, our same assumption is made, is that y is equal to this power series, and then we take our derivatives that we solved earlier, our first and our second derivatives, and plug them into our differential equation. So x times our second derivative plus our first derivative plus x times our no derivative, just our original y function. Now, here we want to bring any coefficients inside the sum. That means these two x's. And so we're going to multiply x times x to the n minus 2. We're multiplying with the same base. We add exponents. Same thing here. X times x to the n. This gives me x to the n plus 1. Now, our goal is to make all of the exponents the same. And so what we're going to try to do is we're going to try to adjust these to make them all x to the n or x to the n plus 1. Just to make the arithmetic a little easier, I'm going to stick with x to the n. And so if I want to make this n plus 1 back to n, I'm going to have to start with n equals 1. And then my Cn will drop down to n minus 1. So we did this process in the reverse direction earlier, but now we're doing it in the opposite order. Instead of lowering this index starting value, we're raising it. This one we're bringing down because we want x to the n. So we're going to start this one at 0, and so this n will become n plus 1. That's what we talked about earlier. And then this one, we're only going to bring down one starting value because multiplying by x, I turn this into n minus 1. And so to make it x to the n, I only want to bring it down by 1. So this will be Cn plus 1. And then this one will become n, and the n will become n plus 1. And then this is our x to the n. Now, again, in step 3, this was a null behavior last time, but now we have to actually do something with it because our indices are not all starting at the same place. So we need to make them all the same, but we can't do it by adjusting the power of x anymore. So instead, we're going to use that second trick we talked about, which is to pull out any the first term, or however many terms we need, of the index that has the smaller starting value. So for our n equals 0 component right here, we're going to pull out that n equals 0 term so that this summation can also start at n equals 1. And so that's what we've done here. We've simply taken our formula, plugged in n equals 0. So when n is 0 here, I get C1, n plus 1, 0 plus 1 is 1, and then x to the 0, which is just 1, obviously. But now, by doing that, all of our summations now start with n equals 1. And so now I can combine them because they all have the same power and the same starting value. And then I'll get this extra stray term out here. Now, I'm going to collect all of these summations together to get a single coefficient and collect any loose terms with the same power. So I only have one loose term, which is just the C1. But then for these other ones, I can add those together. These are my terms from the second derivative. These are my terms from the first derivative, and this is my term from the original function. And so I need all these coefficients to be 0 all the time. So I set my coefficients equal to 0. That means C1 is 0 because it's out there by itself. And also that all of these have to be 0. Again, we want them to be 0 for any value of x. So it's the coefficients that have to work together. And then we can get Cn plus 1, if we do some algebra, to be solved in terms of Cn minus 1. Now, technically, we've got two solutions. Only one of them is 0, which isn't a great place to start. So that solution actually disappears, and we end up with just one solution, which is skipping every other term. So that when we start generating the coefficients, as we did before in our table, for this last case, all of these odd ones, C1, C3, C4, C5, they're all 0. So that's not a solution. But we do get one solution from the other coefficients. So if we start with C0, we can find C2. And if we start with C4, we can find from C2, we can find C4, and so forth. And so we do end up with at least one solution. Now these denominators are kind of insane, but you can rewrite this expression in a nice compact solution. But we can't actually, this is only one solution. We started with a second order differential equation. How do we get that second solution? Well, we're going to talk about that in the last example. I want to do one additional example before we do that, where we're centering at something other than 0, and how to work around that before we deal with Frobenius's theorem in order to fix our missing solution for this example. All right, so example 3. Now we're not dealing with just x's multiplying our derivatives, but now we're dealing with polynomials, essentially, x plus 1 in this case, and 2 minus x. And we want to, if we put this in standard form, the singular point is actually at x equals -1. So we're going to try to solve this at the ordinary point, x equals 1. So we could have used 0 for this. That probably would have been fine. But again, as an illustration of moving the center and solving it at a slightly different point, which is a trick that you can also use for the previous example, we want to look at how that math works out. Now, in order to do that, we're going to need to rewrite all the other expressions, all of the expressions in our equation in terms of the factor x minus 1, where we're centering our approximation, because we're going to want to put these inside of our series solution, and we can't do that if they're not in the form of a constant or an x minus 1. So we're going to rewrite x plus 1 as x minus 1 plus 2. And we're going to rewrite negative 2x minus negative quantity 2 minus x, which is equivalent to x minus 2, as x minus 1 minus 1. And so now we're going to replace our x plus 1 and our minus 2 minus x expressions with these rewritten expressions here. And then again, just to make my life a little bit easier in terms of rewriting this and getting really messy expressions, I'm going to do kind of a substitution, and I'm going to replace x minus 1 with u. The derivative of x minus 1 is just the derivative of x, which is 1. So this is not really doing anything to our formulas. It's just going to mean that I don't have to write x minus 1 all the time. I can just write u. And that'll make it a little bit easier for us to work with it. So I'm going to rewrite x minus 1 plus 2 as u plus 2, and x minus 1 minus 1 as u minus 1. And now I do my derivatives. Again, when I do my derivatives of my y, I've just replaced x minus 1 with u, and that doesn't generate any chain rules or anything. So I've got my u plus 2 times my sum for my second derivative involving u, which remember is x minus 1, and then u minus 1 and my sum for my first derivative, and then my y in terms of u. Now we go through the same steps that we went through in the previous one. We want to combine the coefficients. So we need to split up the parentheses and then plug in our, just add our coefficients into the functions. Now we have to do these, the u's and the constant separately. So that's why I've split these up here. And then when I bring this u in, I get u to the n minus 1. This 2 comes in, but it doesn't change the power. This u comes in and changes the power. This minus 1 doesn't really do anything. And then again, that one doesn't change because it wasn't multiplied by anything. Now for step 2, we're going to adjust the index. So we're going to try to collect everything in terms of u to the n. So this one was fine, this one was fine, and this one was fine. But this one was, we go back up, this one was n minus 1, and so we're going to redo this index to bring it down, and then replace n with n plus 1, and now we're good. Same thing here. This was n equals 2, and we want to change this to u to the n, so we bring our index down, and we replace all of our n's with n plus 2. Now this one, because I multiplied the u through, I can't bring it down 2, but I can bring it down 1, and then replace all my n's with n plus 1. And then the next thing, of course, is to match our starting values. So since the largest one is n equals 1, we're going to, all the ones that start with 0, we're going to pull out a first term. So this one started at 1, so we don't have to do anything. This one had started at 0, and so we're going to pull out the 0th term by plugging in n equals 0 into our formula, and then just rewriting the rest of the series as the summation. So we have our 2, we have our C2 when n is 0, 0 plus 2 is 2, 0 plus 1 is 1, u to the 0. And then same thing, this one started at 1, so we were good. This one started at 0, so we pull out the n equals 0 term. Again, watch out for this sign out here because it distributes, and so both terms are negative. And then this one also started at 0, and so we pull out the 0th term. Once all of our indices start at the same place, we collect our constants. And so this guy, and this guy all end up out here. And then all the summations get added together with the u to the n factored out. And we get this whole mess of crazy. Now we have some Cn plus 1s and things like that. So, and Cn's, and so we can combine those a little bit. The Cn and the Cn plus 1, the Cn plus 1 and the Cn plus 1, we can combine those like this. And then the Cn plus 2 doesn't do anything. It's by itself. We need to come up with our relationships between our coefficients. So all of these guys get set equal to 0. All of these guys get set equal to 0 collectively. And when we do that, we can solve for C2 in terms of both C1 and C0. And then we get this crazy expression that, again, we try to solve for Cn plus 2, the highest index in our expression. Now, essentially, we have two series here. We're going to get coefficients that depend on C0 and C1, right? So if this is C0, this will be C1. And so now we start solving. N equals 0 gives us this expression for C2. but then we go to n equals 1, and so we use our formula, the second one that we generated, this one, and we end up with this C2 expression canceling out, and we have just negative C1 over 2. N equals 2, we plug in C3 and C2. Then we have to replace C2 and C3 with our previous expressions for C2 and C3 because we want a solution in terms of C0 and C1. And so on and so forth. We keep going. C5 depends on C3 and C4, which we can rewrite in terms of C1 and C0. And then we can actually separate out our C0 and C1 coefficients into two separate sets. So Y1 is going to be C0, again, times 1, because that's the first term in the sequence. And then the coefficients that come out of C2, C4, C5, etc. And the U, of course, is actually x minus 1. So this is our original, in the original variable, our Y1 expression. And then for Y2, we use where the C1s are. The starting value is the original linear term because that subscript agrees with the power, right? So C1 times U, and then we have a coefficient for the second term, C2, C3, etc. And then the U's, of course, are replaced by x minus 1 powers. If you look at these, there doesn't seem to be a nice way to rewrite these in a nice summation formula. And so sometimes that happens depending on how messed up your differential equation was. And so we're just going to leave it that way. Now, as I mentioned before, we're going to return to this, the second example, and try to solve it, actually get two solutions. Since x equals 0 is a singular point, we have two options. We can shift the center and try to solve it at a different location, or we can use this trick called Frobenius's theorem, where we can use that to try to generate a second solution. And what changes is that we're going to multiply our solution by some unknown power of x. So we're going to conclude that y is equal to this summation, this power series. And the difference is that instead of x minus x of 0 raised to the n, it's now raised to the n plus r. Again, we're going to center this at 0 using this trick. That's the example that we're going to walk through. So again, we will take the derivatives normally. This will replace anywhere we had an n with n plus r. And then, of course, n minus 1 would be n plus r minus 1. Same as our first derivative. Bring down the n plus r, subtract 1. And then this was just our original solution. We've got our x's here from our original differential equation. Now, if we're going to try to factor out x to the r as much as we possibly can, then it can't be equal to 0 anywhere. So we pull that out. And that leaves us with, now again, the x to the r can come out. The other r's can't come out, but x to the r can come out. And that leaves us with this expression. So all the x to the n plus r minus 2's become just x to the n minus 2's, and so forth. And then we can continue with our process the way that we did before, more or less. So we've got our summations. We want to bring our x's inside of the summation. So this x out here, bring that inside. This x out here, bring that inside. We can make all of our powers x to the n so that they're all the same power. Again, this is the same thing that we did in the previous step. Again, the only difference so far is this n plus r instead of just n. The next step, again, follows the same as before. We try to make all of the indices equal to the same starting value. So the one that starts sooner, we bring out the leading term by plugging in n equals 0 and then leaving the remaining terms inside the summation. And then step 4 is we collect everything. So we factor out our x to the n. All of the coefficients that go with our x to the n's all go together. And then our one loose term is out here by itself. Now we set the coefficients equal to 0. The loose term, we set that equal to 0. And then this string of coefficients from our summation, we set that equal to 0. Now, the difference here is that in the C1, we have two ways to make this 0. Either r is equal to -1 or C1 equals 0. Now, if we go down the C1 equals 0 path, that gets us our only one solution that we saw in that second example. So instead, we're going to choose r equal -1. And that will give us C1 not being equal to 0. It'll be equal to something. And the second expression we solve for Cn plus 1 in terms of Cn minus 1, similarly to the way that we did before. Obviously, the expression is a little bit different, but that's what we do. And then once we determine that r is equal to -1, then we can plug that into the expression, and that gets us a new expression where Cn plus 1 depends on Cn minus 1. That'll get us our two sequences of terms. One of these will be C0, one of these will be C1. And so now we can build our table of coefficients. When n is 1, C0 is Cn minus 1. So that gives us C2. And we get an expression in terms of C0. N equals 3 is going to give us C4 in terms of C0. N equals 5 is going to give us C6 in terms of C0. Again, first plug in C4, then replace C4 with your expression for C4 in terms of C0, and on for as long as you need. And then for the other side, when n is equal to 2, that's going to give you C1, C3 in terms of C1, and then C5 will be first in terms of C3, which you then substitute in terms of C1. And again, you get this string of coefficients. Now again, notice these coefficients in the second side here, these are consistent with the answer that we had before. And these ones are the new ones. And so y2 is our solution that we had before. And then y1, the new one, is this solution here. We've got these crazy odd powers. And it's a messy expression. You can't actually write a nice formula for it, but it's a terrible formula. But even though there is a general formula. All right, so this is how you solve differential equations using series solutions.